it is clear why we cut them out, and what these were. Basically, as I said in my previous videos or earlier in this video, that this is the way that we can find distance of a point from a line. So this is the way, and now we have solved almost all of the problem that we have in this part, but still this is not going to work. Let me explain you why this is not going to work. Because we are going to use the gradient descent. Okay, so as we have this part, we have to minimize this. So let's suppose we are using this, and we are minimizing this part. Okay, and what we are doing is we are going here, we are going here, we are going here. But even this, what we have is that we have this constraint. We are saying, okay, minimize this, but you should have, you should follow this condition. If you are not following this condition, then you cannot minimize further. So there is a limit to this, and it cannot minimize it further. So this is the main problem behind this part, and we cannot even solve it like this. Okay, so for that, what we are gonna do is we are gonna use the primal form. So what we are gonna do is that we are gonna introduce a slack variable, or you can say that we are gonna allow some error to happen. So for that, we have to understand the concept of outliers in SVM. So yeah, so we have these points, let's say, and so if we were talking about SVM, so the best way to define this would be uh, literally, like, you cannot create a straight line, or if you can create a straight line, it would be something like this. But this is not a very good line. Okay, and the reason I'm saying that is, if you'll see, each and every point is like this side, but only one point is here. So if we will not allow this point to have some error, so what it is going to do is that it is going to affect every other point. Although majority of data is this side, but this single point is affecting every other point. So what we are going to do is we are going to make a line like this. Okay, and in this part, let me also close this. So this is our support vectors, and so if you will consider this, this is called as outlier, because it should be on this side, but it is this side. So that's why it is called as outlier. And what we are gonna do is we are gonna allow some error. That okay, we are gonna allow some error, and it can be on this side, but it will have some error value. Okay, so for that, what I'm going to do, I'm going to change this formula first. So what it is going to be yi w transpose, or you can just leave the yi for this now, wt x plus b should be greater than 1. But what I'm saying is that I can allow some error. So I'm going to divide this ei by I. You can just take this. Yeah, so we are saying for every point we can allow some error here. Okay, and this is also called as a slack variable. So for now, you just have to understand this. Now if we are changing this, then this equation is also going to be changed. So this equation is now going to be let's suppose 1 upon 2 square. And one more thing, let's not take this. First, let's not take this. What I'm going to do is, this is very difficult to solve. So what we are going to do is, I'm going to take the square of this. That square is going to be w transpose w. And when we are gonna take the differentiation, then it is going to be very easy. But if we had take that, then it would have been very difficult. So that's why what I'm going to do is I'm going to take the square for this. So our output will be W transpose W. Okay, so what I'm going to do here is our formula will change something like this, half W transpose W. And I'm going to say okay, this is, we want to minimize this, but we can minimize this with the some cost, and that cost is going to be affected by the error value. So for every error I equal to 1 to m, we are going to add this. Okay, so what we are saying is that okay, we have this uh, here, but what we are saying is that if if we have some error, then that error is going to be used here. Let's suppose if a point is on this side. Okay, if a point on this side, then that error is going to contribute nothing, because that error is going to be 0. But if some point is here, then that error is going to be contribute to something, and c is a hyperparameter, so you can change the value of c to see uh, whether it how it works like. Okay, so you can increase or decrease its value to see when it is giving the optimal performance. So now what is the c? Let's suppose if you are taking c a very big value, let's suppose you are taking c as infinity, so you are not going to allow any outliers. Okay, because you want to minimize this part. And if you are taking c as a infinity part, it means that you cannot minimize this, and that is going to be very big, so you will not take any, you will not allow any error. Okay, but if you are taking c a very small value, then what you can do is you can allow some error here. So that is how c is going to be c is going to affect here. Now as we have done this, what we can do here is still there is a problem, is that we are still having a constraint here. So what we can do is we can change this equation again. So in this here we can say ei is going to be less than equal to 1, and 1 minus yi w t xi plus b. Okay, so you can say that okay, ei could be this, and what we are gonna do is we are gonna implement that value of ei in this part. So our equation is going to be, let me start this all. So our equation is going to be 1 upon 2 w transpose plus c sigma I to 1 to m, and here I am going to apply the value of this. So that value is 1 minus yi wt xi plus 2. Okay, so this is the value that I have done here, and let's take this value as ti. Okay, so this value is being taken as ti, and what you can do here is, oh yeah, we also have one condition, is that ei should be greater than equal to 0. So the error should be greater than or equal to 0. Error should never be in negative part. So here we also have this condition. So what I'm going to do is we can say we have to take the biggest error. So what we can say is that c sigma I equal to 1 to m. What I am going to say is I'm going to say maximum of 0 and 1 minus ti. So instead of taking this part, we are taking this part. So let me explain this once more, what is happening here. Let me stop this. So as we said that we have this, we have this, we have this support vectors like this, this, and let's suppose in this side we have circles, this side we have x, 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 and we have, let's suppose, this outlier here. So what we are saying is that error either should be 0 or, so the value of this is going to be, let's say, ti. What is can be the value of this? So let me scrub this. Yeah, so if you will consider this part, and this is either going to be -1 or +1 on the basis of whether this is a negative class, or this belongs to negative class or positive class. Okay, and now what I'm saying here is that if ti value is greater than 1, let's suppose it is let's suppose this gives a value of -2. Okay, and that -2 is multiplied with -1, so it is going to be 2. Basically it means that the distance is this side. Okay, so what it is going to do, okay, we say that this distance is going in negative. It means that we do not have to worry about this, and our output is going to be 0. But if it is less than 1, it means that what it is, it means that, let's suppose it is 0.8. okay, so minus 0.8 is multiplied with -1, it is going to be 0.8, and this value is -1 plus 1 or 0 and 1. So 0.8, when we are talking about the distance, so this is 1 unit, and we are talking about 0.8. so let's suppose we have some data here, so this is also a outlier. So in this case we have to consider this part. So I hope that this is clear how we got to this formula, and you can watch this video 1-2 times to understand this part, and it is pretty easy. So this was it for this video. Now what you can do is that you can use this formula as your error function, and you can minimize this so that you will get the optimal values of the line. And what you can also do is for the gradient descent, you have to take just the w values like this. So that is going to be let's w equal to w minus n delta of w. Here w is this whole line, okay, this whole loss. So this is what we are gonna do here, and thanks for watching, and I'll see you next time.